Good morning to everyone. Today we have the third lecture of Professor Naidon. Professor Naidon, you can start.
Okay. Oops, sorry. Okay, so sorry. All right. So in this lesson we will so previously we saw in details the Efimov effect and how it works, and we derived all the formulas and everything. And in this lesson, we'll have a bit more relaxed view at now the experimental observations of this Efimov physics, and more generally how we can have not only three bodies but universal clusters of particles that follow that have some universal properties related to the Efimov effect. So I will start with giving a few examples of experimental observations, and then we'll look at mixtures of particles. Okay, so let me start. So what we've seen so far is the case of three bosons, right? And this is the what we obtained in the previous lesson, that close to the unitary limit, where the two-body bound state appears, there is this three-body spectrum with an infinite series of three-body states that are the Efimov states. So as it was pointed out, there's an infinite number of states only at the unitary point here when the scattering is infinite. In reality, the scattering of a given system is fixed at some particular value, and usually it's away from this unitary, from this universal region. But for some systems, it comes close enough to enter this universal region. So an example I mentioned before is the case of the triton, which is the bound state of 2 neutrons and 1 proton. So for this system, the relevant scattering length is the triplet scattering length, which is positive. So that means that we are on this side, positive scattering length, but it's not sufficiently large to enter the regime where there are several three-body bound states. So there's only one three-body bound state. And this three-body bound state, which is the triton, well, it correlates to this Efimov scenario, as we will see. A better example is the case of helium-4 trimers, so trimer made of 3 helium-4 atoms. In that case, the scattering length is a bit larger compared to the range of the interactions, which means that we are now sitting here where there can be 2 Efimov states. And we'll see that indeed there are 2 observed trimers for this physical system, and they correspond roughly to this Efimov series, although the as we'll see, the excited state is the closest to what we might call an Efimov state. And then so there are examples in nature, but as I mentioned, it's also possible to observe Efimov physics in ultra-cold atom systems. And in these systems, the great advantage is we can actually change the scattering lengths between the particles, between the atoms, through the Feshbach resonance, as I explained before. And so that means that we can further explore this spectrum and get closer to unitarity. So what has been observed in particular is these points where the trimers dissociate into the three-body continuum. So I will explain how this could be measured. And it was even possible to measure on the other hand, on the other side, the points where the trimers dissociate into a dimer and a particle. with this autocool atom experiments. So let me start with the triton. So here on this graph, what I've shown is the, so first look at the dashed curves. So they correspond to the two-body bound state and three-body bound state that you would obtain in a zero-range theory. So if you set up a zero-range theory for this particular system, where you input the so the physical parameters of the scattering length, the triplet and singlet scattering lengths for the system, then you obtain these curves. And you see that there's a ground state here, and there's an excited state which is barely visible. Maybe you can see a little bit. But so that's assuming that we can change here the triplet scattering length. The physical value of the triplet scattering length is indicated by this red line. But as you can see, these 2 points here are the experimental observations of the deuteron energy and the triton energy. And they do not quite match this zero-range theory. So it means that even though the scattering length is relatively large compared to the range of the interactions, we are still in a region where deviations from the universal theory are strong. And the dash curve, the solid curves here are the curves that one obtains when one uses finite range potentials, more precisely taking into account the effective range of these interaction. And then you get much better agreement for the deuteron, and you get also better agreement for the triton, although you can see that it's not perfect agreement. So this could be improved by including, for example, a three-body interaction, and with a three-body interaction, you could match perfectly this point. But as you can see, the triton and deuteron are consistent with this general predictions from the universal zero-range theory, but mostly qualitatively. So yes, it's qualitatively consistent, but not the best example. And also one drawback is that we only have one trimer state, so it's difficult to, I mean, as theorists, we can imagine that we can change the interaction, but you know, you can understand the properties of the deuterons and the tritons without ever thinking about this Efimov scenario. You don't need it to explain the properties of the systems. Okay, so let's look at another example, which is the case of the HOI state of carbon-12. So you probably know about this state because it's quite kind of important in astrophysics. And in the original, so this is an excited state of carbon-12 that is believed to be a form of 3 alpha clusters. And in the original paper by Vitaly Efimov, where he described this, the Efimov effect, he suggested that this HOI state could be the result of, so if we regard it as a three-body system and assume that it is in the condition for the occurrence of the Efimov effect, which means that the interaction between these alpha particles is nearly resonant, then he conjectured that the state could be the result of the combination of this Efimov effect and the fact that there's also Coulomb repulsion between these particles because they have positive charge. So this is a very simple and elegant idea. So there would be this 1/r squared effective three-body attraction, as we have seen. And in addition, there would be some 1/r Coulomb repulsion. And the result would give this curve, which which has a barrier here. And so without this, the Coulomb repulsion, there would be a bound state here. And because of the Coulomb repulsion, this state is pushed to positive energy where it becomes a resonance just above the threshold. And that would correspond to the HOI state resonance of carbon-12. So this is a very, very, I think, interesting idea. However, it seems that it's unfortunately not very likely that this picture can explain the HOI state of carbon-12. Here I presented very, very simple, simplified model where everything is just described in terms of the hyperradius. So there's just a model potential for the Eufim of attraction and model potential for the Coulomb repulsion. But playing with the simple model, you can see that in order to reproduce the energy of the HOI state, which is right here, one needs to tune the short-range boundary condition that sets the Threebody parameter. As you remember, this 1/r² potential is not well defined if we do not impose some physical boundary condition at short distance. And this condition turns out to occur at a very small hyperradius that is actually smaller than the physical range of the nuclear force. Of course, that's not impossible, but it seems that when you look at this kind of model, it seems quite unlikely that it's possible for the nuclear interaction to create this kind of boundary condition. Also, there's the question whether this interaction between alpha particles with a Coulomb interaction is near resonant. That is not quite clear. And it looks like this HOI state is actually, in this nice picture, the HOI state would just be described by some kind of long-range Eufim of attraction, which is purely kinetic, as we've seen, and this Coulomb repulsion. But actually, it looks like it actually it enters a region where the nuclear force cannot be regarded as a contact interaction. It really occurs in the range where the nuclear interaction is essential. So it appears unlikely that this picture holds, but it's nonetheless a very interesting idea in general if one could find similar states that are kind of long-range states that the consequence of just some Eufim of attraction occurring at large distance compared to the range of interactions and an interplay with the Coulomb interaction. Okay, so no clear evidence. Okay, now we come to the case of the helium triatomic molecules of helium-4. So again, I've made a similar plot as in the case of the triton, where I represented the zero-range theory with this long dashed lines. And that is, as always, as a function of 1/, the scattering lengths between the helium atoms. Of course, in reality, so this is, again, some kind of physicist, theorist's vision. In reality, the scattering lengths of between two helium-4 atoms is fixed at this physical value. And we can see that now in the zero-range theory for this particular scattering lengths, we have two trimers. And indeed, it was observed that there are indeed two trimers in the system. So a grand trimer and an excited trimer. And so I didn't mention that there's also a dimer, helium dimer. And you see that here, that now the zero-range theory is in better agreement with the experimental data when we compare to the Triton case. The ground state is not so good. It can be improved if we use this what is shown by this dashed and solid line. These are finite range interaction models, and they get a bit closer to the experimental data. It turns out that and that's a generic feature, that ground state of such system, especially when it's down there, quite bound region, is relatively different from what you would expect for an Helium state described by the universal zero-range theory. However, the excited state is much closer and can be regarded as an actual Helium state. So the experiment that revealed these states was done in Frankfurt in the group of Reinhard Döhner. So I think maybe you will have I forgot if you already had it, or the Professor Dorte Blumer will describe this experiment in detail, because she was involved actually in the theoretical analysis of this experiment. But let me explain briefly how it works. The experimentalist creates some kind of molecular beam of helium-4 atoms. And in this beam, there can be some, they are mostly atoms, but sometimes they combine to form a helium dimer or helium trimer. And using some kind of grating, it's possible to separate these different contributions, so the atoms, the dimer, and the trimer, and they are deflected in different angles. So by selecting a particular diffracted beam, one can obtain the beam of trimers. And then on this beam, there's a femtosecond laser that is very strong, that is applied onto this beam of triatomic molecules. And essentially what it does is so strong that it strips out the electrons from this molecule. And so what remains are just the nuclei, and and by Coulomb repulsion, they go away from each other. This is called the Coulomb explosion. And then the resulting ions are detected on this ion detector. And from this detection, it's actually possible to reconstruct the motion of these atoms, which is essentially classical. And then one can reconstruct the original position of these atoms when they were hit by the lasers. And by repeating this experiment, it's actually possible to reconstruct the probability density that is associated to the wave function of this triatomic molecule. And so these are the results. Here is the theory for the excited state theory for the ground state, and here is the experimental result for the excited states. Right, and so I will not explain in detail, but this is a way to represent this density, probability density for these three ions when they hit the for the three atoms in the molecules when they were hit by the lasers. And so essentially we have the first atom, second atom, and third atom, something like this. Right, and you see there's a good agreement between in this representation, there's a good agreement between the theory and experiment for the excited state. That's another way to represent the geometry of this system. You see there's higher probability in these regions, which correspond to some kind of elongated geometry. And that's consistent with what we, so this is the experimental data, and that's consistent with what is predicted by the theory and what we saw also in the zero-range theory. So from this, we can see that the excited state of this triatomic molecule is well described by this, can be regarded as an Helium state. It is less so for the ground states. These are the this is the theory prediction for the ground state, and you can see that if we compare. So I have to mention these are not the. So here this is the same scale, but here this is not the same scale. You see, this is much larger. This is much smaller than this one. So the extent of the state is much larger, as you would expect, because it's much more weakly bound state. Much more difficult to observe, actually. The ground state was observed many years ago, but it took a long time to actually be able to observe this excited state because it's so large and so weakly bound. But anyway, you can see that in terms of geometry, there's a rather clear difference between this excited state and the ground states. Where essentially for the ground states, any geometry is has the same probability essentially, which is quite different from the expectation for a real ephemeral state as it is described in the zero-range theory. So this is an important difference between the ground state and the excited state. So some people sometimes call this ground state the ground state of the ephemeral series. Some people say that it's actually not an ephemeral state. So it may be a matter of taste depending on what kind of observable you look at. But as you can see, there are clear differences. So here I just wanted to give you just a sense of scale, just a simple animation, just to show you what does an ephemeral state look like in the context of this helium triatomic molecules. So for comparison, I showed here a typical usual triatomic molecule like this ozone molecule. I could have also taken the water molecule. Well, here we have identical atoms, so 3 oxygen atoms. And this kind of state is tightly bound. And it has a relatively well-defined geometry. So the separation between the atoms and the angle formed by these 2 arms here is relatively well-defined. Of course, there are some fluctuations, but they are fairly small. So this kind of molecules, like most molecules, have rather well-defined geometry. Now, if we compare with the ground state of the helium trimer, it looks like this. So we have the another thing I should have mentioned is that the atoms essentially touch each other such that the electrons, the electronic clouds of these atoms merge together to form an electronic cloud around the whole molecule. And this is actually what holds the system together. But in the case of the helium trimer, the helium atoms are relatively well separated from each other. So they remain bound, but over much larger distances, as you can see. And as I explained in the previous lesson, the binding is not so much due to the exchange of electrons like this usual covalent bonding, but it's rather due to this kind of quick motion of one of the atoms moving between the 2 others and in a sense mediating a kind of interaction between these 2, and this repeated process holds the whole system together. So it's a very different binding mechanism than the usual molecules, which relies really on the exchange of electrons, where here it's more like the exchange of atoms themselves. So again, this ground state is not probably cannot be regarded as a true ephemeral state for the reasons I explained before. But yet you see it's markedly different from the usual molecules. And now if we go to the excited states, then we have an even larger molecule, of course. And here it really behaves like an ephemeral state. As we could see in the figure, most of the time, if we take a snapshot of this state, we find elongated configuration, which was seen in the experiments. So this is a nice example of ephemeral states. Okay, so now I come to the observations in alcohol atomic gases. So in the previous lesson, that was in the first lesson, I explained a little bit the context of this alcohol atomic experiments. Now so as I told you, these systems are very nice because we can actually change the scattering lengths between the atoms by tuning some magnetic field that is imposed on the system. So we can actually go further than these previous examples that I showed you, and we can actually explore this whole spectrum. What has been done a lot is to look at the Threebody recombination rate. And this enables to see signatures of this ephemeral trimers. So let me explain. Forgot if, well, no, I don't have any graph to explain. So let me explain just by hand. Essentially, these atoms, they actually have fairly deep potentials, interaction potentials. So they have a lot of bound states, in particular two-body bound states. So when when three of these atoms collide together, they can two of them can actually go to a two-body bound state, and the released energy is imparted to this new formed two-body bound state and the remaining third particle. So this is an inelastic process where the three particles come together, and then two of them form a two-body bound state, and then they go away using the energy that is released by this process. So that's something that occurs in all these ultra-cold atomic experiments, and that's usually a source of losses, because the kinetic energy that is imparted to this two-body bound state and atoms are fairly large, usually compared to the trapping energy of the system. So it can usually exceed the energy of the trapping. And so that means that these atoms and dimers, two-body bound states, they can escape from the system and they're essentially lost. So if one simply measure the number of atoms in the system, one will see that generally it tends to decrease over time because of these loss processes. And then one can characterize the strengths of these losses by looking at the decay of the number of atoms, and this decay will behave differently depending on the value of the scatterings between the atoms. So generally speaking, as we come close to the unitary point where the scattering is large, there will be strong enhancement of these losses by recombination. And the reason is because as we increase the scattering lengths, we increase the probability for two particles to be together. That's something that you can see in the wave function that we plotted for in the first lesson for the two particles with large scattering lengths. There's a huge hump of probability density that increases the presence of the particles to be together in a range where they can actually undergo this kind of inelastic processes. And now there's on top of this general, this global peak of the losses, there are some sub-peaks like this. And these are due to the presence of Threebody bound states. And the reason is because when three particles collide together, and there's a Threebody bound state is present, then their Threebody probability is also increased by this the presence of this state. As you might remember, I showed in the previous lesson that these Efimov trimers, they not only form bound state here, but they extend at positive energy as some kind of resonance. So that means that when the three particles come together around these points, then they enter this resonance for some time, and they stay a longer time together in a region where they can undergo these inelastic processes. And so that results in an enhancement of this inelastic process, a local enhancement whenever the scattering length is close to the point where these trimers appear below the threshold. And so this could be seen experimentally. So here I show the results. The first, so this is the case of bosonic cesium atoms. These experiments were realized in Innsbruck in the group of Rudolf Green. So here you have this rate for this recombination that was measured experimentally as a function of the scattering length between the cesium atoms. So again, this is changed by changing the value of the applied magnetic field. And they could observe in around 2006 a first resonance that is associated to the first trimer here. And then some years later, in 2014, this was much more difficult to observe. They had to go to very low temperature, and there's a lot of technical challenges, but they were finally able to see a second peak that is associated to the second resonance. And very interestingly, the location of these resonances in terms of scattering lengths, if you take the ratio between the location of the scatterings for this resonance and the scatterings for that resonance, it turns out to be 21.0 plus or minus 1, which is within the experimental uncertainty close to the, no, actually, yeah, the theoretical value is 22.7, or it's at least very close. So here I show you a picture of Vitaly Efimov when he visited Grimm's group. And for this nice theoretical prediction by Vitaly Efimov and nice experimental confirmation, these two researchers were awarded the first FADEF medal in COE in 2018. Okay, so there have been other observations in ultra-cold atomic gases. Here I mentioned an observation with three distinct, so not bosonic atoms, actually fermionic atoms, but in that case, these fermionic atoms can be prepared in three different internal states. So this is lithium 6 fermionic atoms, and they have different hyperfine states, and the experimentally it's possible to select three of these hyperfine states. So in this way, these atoms, although they are fermions, they essentially behave as distinguishable particles, and they can have symmetric wave function like the bosons, and they can undergo the Efimov effect. So they almost behave like bosons when there are just three of them, except that they have different scattering lengths for each pair. So the scattering length between 1 and 2 is not the same as 2 and 3, etc. But it turns out that all these pairs become resonant in the same region of magnetic field. So here, this is the magnetic field, and around this, between this 600, 800 Gauss, there are resonances for these three pairs. So here there's resonance for the pair 1, 3, for the pair 2, 3, 1, 2. So this is the points where a two-body bound state appears for each pair. And around these resonances, then we have a universal region that is indicated by this white area, where the physics is expected to be described by the universal zero-range theory. So for the three interactions. And interestingly, it is also the case in this region. What happens is that the scattering length here is, when you have a dimer, that means the scattering length is positive, very large, and then it becomes smaller and smaller as we go away from this unitary point. And then it becomes 0, and then it turns negative, and then it becomes very large and negative. There's another resonance, in a sense, that would exist at negative magnetic field if that were possible. But the result is that you have a very large negative scattering length for all this interaction in this region. And so there's again a universal window in white where there can be universal physics. And historically, what was measured was the three-body recombination rate in this region, and the experimentalist observed one peak here and something that looked like a peak, which is a bit broader. And assuming that this is due to some Efimov trimer, because we're in this universal region, it's possible to actually, you remember in the zero-range theory, there's a free parameter that is the three-body parameter that has to be set by hand. So if we don't know this three-body parameter, we cannot make predictions. That's one of the difficulties to actually identify Efimov states in physical systems, because the three-body parameter is usually unknown. But here we have some experimental data where we can assume that this is due to a three-body resonance. And therefore, theoretically, it's possible to adjust the three-body parameter and use the known two-body scattering lengths to deduce the three-body spectrum. And indeed, if you do so, the theorists could find that there's if a three-body bound state appears here, then it would behave like this. So this would be a Borromean, in the Borromean region of Efimov states. So I cannot really make a connection with the plots I've shown you before boson, because in that case, there was only one scattering length. Now we have three scattering lengths, so it would be some kind of a three-dimensional plot. But so here I just plot the as a function of scattering length of a magnetic field, and all these three scattering lengths are changing with the magnetic field. And the result is that you have a Borromean Efimov trimers that appears at this point. So this is by construction to fit the experiments. And then it should, interestingly, its binding energy decreases at some point, and then it dissociates again at another point. And that corresponds to the point where there was also some kind of broad peak here. While using some kind of refinement in the theory, it's actually possible to more or less reproduce this, what happens here with this kind of assumption. But now what's interesting is that once you have fixed the three-body parameter in the model, it's actually possible to make predictions for what happens in this region, assuming that it is the same three-body parameter that is here in this region and in that region. So the prediction is that there would be two Efimov trimers in this region. So a ground state here and an excited state. And this one would just dissociate into this 2,3 dimer, and this one as well. But this one also dissociate at the three particle threshold. And it's possible to also predict the rate of the losses by Threebody recombination, and one gets a curve, some curve like this. And indeed, the experimenters were able to confirm this prediction by making measurement in this region, and that was in agreement with the presence of a peak here. So, so it's an interesting story how the experiments led to theory, which eventually led to experimental confirmation.
Professor Naidon,
yeah.
Tobias has a question. He wants to.
Okay.
Tobias.
Yes. Pascal.
Yes.
I was wondering about this point of the same Threebody parameter, because I mean this physics
yes.
of the fetch bar resonance seems quite complex. Why this cannot be changed, these Threebody parameters, when you move?
Yeah, you're right. Actually, so that was an interesting question, and indeed, it was not granted that it would be the same Threebody parameter in these two different regions. But as we will see in the next lesson, actually, it was later found that for these hemostates with atoms with this kind of these are quite broad resonances, actually very broad resonances. It was found that the Threebody parameter is actually determined by the length scale associated to the interaction between the atoms, which is the Van der Waals, the so-called Van der Waals length. And so that's one of the reasons the Threebody parameter is the same in these two different universal regions, is because they are described by the same Van der Waals interactions at large distance, and this is actually for this particular system, this is what sets the Threebody parameter.
Okay, thank you.
So shall I move on? So that these were the observation with the by looking at the Threebody recombination, the losses by Threebody recombination. So as I said, experimentally, it consists in essentially preparing the system and observing the loss as a function of time, measuring the corresponding loss rate, and then plotting this, and then repeating the experiment for many different magnetic fields, and plotting this as a function of magnetic field. But then it was possible to actually measure what happens in this region here, where the Helium state dissociates into a dimer plus an atom, and to confirm again this theoretical description. So this was done also. So these experiments were done in the United States, in Germany, and also in Japan. So this is the result from the German group, so in this experiment, they were actually able to measure the energy of this ephemeral state close to this dimer threshold. So let me explain briefly how this works. So as you remember, we have three different kinds of atoms corresponding to three different hyperfine states. So we can label them 1, 2, 3, or red, blue, green. So if we have these three different atoms, they have a particular energy, and then two of them, 1 and 2, they can bind to form a dimer like this. And this has a lower energy when we consider the energy of this dimer plus this remaining particle 3 that is unbound. And then if the 3 particles bind together to form the CFR trimer, they have an even lower energy. So that corresponds to the to this situation here. We have the dimer and then we have the trimer. Now, if we this atom 3 here, if this atom 3 is actually not in the third hyperfine state, but say the second hyperfine state, then it turns out that the for this this hyperfine energy are much larger than this binding energies. And so if we consider now the dimer of 1 and 2 and another atom in state 2, this has a much lower energy, which is down there. So then what one can do is to apply some kind of resonant radiation, some RF field to drive transition between these states. So, so first of all, you have to prepare the states. So experimentally, that means that you start with you prepare all the atoms in a particular state, and then you drive them such that you have you can transform some part of them into another state, so that you end up with an unequal mixture of particles 1 and particle 2. So you have an excess of atoms 2 and a minority of atom 1, and then you use the magnetic field to bind these 2 particles by using some kind of adiabatic method. So the idea is that you start in a region where the particles are unbound, for example here, and then you very slowly change the magnetic field such that adiabatically these atoms 1 and 2 gradually bind into this 1,2 dimer. So then you're left with the mixture of 1,2 dimers and the excess of particle 2. And then you can shine this, you can apply this RF field that is resonant between the state 2 and state 3. So what you would see is now if you image the number of remaining atoms in state 2, you would see a signal corresponding to this transition, the conversion of atom 2 to 3. Then you lose some atom 2, so you see some loss like this. But then what you will see other peaks, and they correspond to transition when you go to this state, where you actually not only you change the state of this atom from 2 to 3, but you also bind these two. Sorry, I'm sorry. I got it backwards. So in this case, you have enough energy to actually separate the three particles, and for that transition, you simply change the state of this remaining atom. And then there's a smaller peak here that corresponds to the transition where you can actually associate the 3 atoms together. And so this is the interesting feature. It's more difficult to see experimentally. As you can see, the peak is smaller because it involves these 3 particles, but it can be seen. And this is how they could measure this is how they could make these measurements. So, I mean, if you look in detail, the zero-range theory is not perfect. There are some significant deviations, but I forgot the numbers, but maybe 10% or 15%. But overall, there's a relatively good agreement with the general scenario predicted by the zero-range theory. So mostly everything is well described, is relatively well described by this Efimov scenario. And of course, the deviations from the universal theory is the fact that we are never perfectly in the conditions of the Euler-Lorentz theory because of the finite range corrections and everything. Okay, so are there any questions so far?
Pascal, I have.
Yeah. Yes.
I don't know if someone raised their hand. It's just going back to the transparency where you show the peaks, the recombination peaks. I just wanted to ask something about that. No, no. No, the one, I mean, previous one.
This one?
No, no, go back, a little bit more back.
I think that this is my first slide.
Yes, 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 this one. You have the Borromean side, the negative scattering length.
Yes.
And you have the positive. I was just wondering, what is the meaning?
You're right.
That you pointed out. I was waiting.
Yes, that's right. So this corresponds actually to, so here we have an enhancement indeed of the recombination loss. And here we have some kind of, how to say, suppression. And that corresponds to some kind of interference in the pathways of these three particles colliding. You can actually there are two pathways. They can either collide and go back immediately, or they can go to shorter distances and then go back. And these two paths actually may interfere at particular value of the scattering lengths, and that of course follow the theme of scaling. And so at these points, there's a reduction of probability that prevents the three particles to be at short distance where they undergo these inelastic processes. So that leads to a reduction of the recombination rate.
Okay, so this has to do with a dimer and a particle colliding or not? Or
no. Sorry, this is
colliding.
Still three particles colliding, right?
Colliding.
That's right. So these, yes.
And the scattering amplitude between them has a 0 or something like that.
The scattering amplitude.
Yeah, between the three, or I was trying to associate in this way.
You mean the Threebody scattering amplitude?
Yes.
Yes, that's right. So that's right. There's a kind of suppression of this amplitude near these points.
Okay.
And yes, you're right actually. So first of all, I should say these dips have been seen also experimentally. Probably I don't have in these slides I don't have graphs that show these dips, but they've been seen experimentally. And also, as you mentioned, it's also possible to see make experiment with the dimers. I skipped this point, but before the experimenters could observe could do the spectroscopy with this RF technique, when they prepare the dimer, then there can be collisions between the dimer and another atom in the gas, and then they can how to say, relax to some deeper state. So that these dimers, as you recall, they are halo dimers, so they are very excited, very large dimers, and when they collide with another atom, they can relax into some more deeply Threebody bound states. And so that's another loss process, but now that involves the collisions of dimers and an atom. And so for this, you have to prepare the dimers, like in the last experiments. So this has been seen also experimentally. So you can also, so close to these points here, you can also see some peaks that correspond to an enhancement of these losses close to these points.
Okay, yes, when you have the bound state at exactly the scattering threshold.
Right.
So it's some kind of analogous of the other peak. in the
Absolutely.
Bologna region.
Yes, yes.
Thank you.
Well, it's now it's more, I would probably say, I think it's more analogous to this global peak, because you see this is due to the large scattering lengths between the two particles. And here also we have large scattering lengths between the dimer and the particle. So probably it's more similar to the, here we really have a resonance. Here I think it's due to the large scattering lengths between the dimer and the particle. But anyway, the final effect is similar, that we have an enhancement of these inelastic processes.
Okay, thank you. Thank you, Pascal.
Okay, so now let's move on to, so these were experimental observations for these essentially bosonic systems, although the last example was not quite bosonic system, it was a system of distinguishable particles, so it's a kind of more general case. Okay, now I will go back to theory and show you the various predictions that have been made for different kinds of, yes, we can make, that's right, we can make a break now. That's a good time to make a break.
Okay, so we return in 5 minutes. What?
Mm-hmm.
Okay, in 5 minutes we'll be back. Okay, so we continue now with the class of Professor Naidon.
Okay, so can you see the screen?
Yes.
Okay, good. So now, yes, so now let's look at various predictions that have been made for various mixtures of particles and larger number of particles. So I will start, first I will consider still identical bosons, but now we add one more boson, so we have 4 bosons. So we already know the Threebody spectrum is like this, and then an early question that emerged soon after the Yefimov effect was discovered is whether there can be a 4-body Yefimov effect. And actually, so just 2 or 3 years after the first paper by Yefimov, Amado and Green found that there's no n-body Yefimov effect for n larger than 3. By n-body Yefimov effect, they meant that there's a close to the appearance of n-1 n-1 state with n-1 bosons. There is not an infinite number of n-body states that appear just at this particular point. So that would be a generalization of the Yefimov effect for larger number of particles, but that does not occur. But still, the question remains: are they 4-body bound states, and can they be universally described by some universal theory? And in that theory, do we need to input a 4-body parameter like we needed for the 3-body bound states? This question were not answered at the time. And what was found eventually is that through several works is that there are in fact 4-body bound states, and interestingly they are related to the Yefimov trimers. So what it means is that, for example, close to this ground state Yefimov trimer, there are 2 4-body bound states. So there's a ground state here and an excited state which is very close to this 3-body threshold, trimer threshold. So it may be regarded as a trimer that is loosely bound to another particle. And the interesting thing is that this pattern repeats itself for each Yefimov trimer. So for all the excited Yefimov trimers, there are also 4-body states which follow the same structure. So as you can see, these are not 4-body Yefimov states, because in the meaning given by Amado and Green, that would mean that there would be an infinite number of states close to these points, but that is not the case. There are just 2 4-body states, but nevertheless they follow the Yefimov scaling. So this is not really a 4-body effect, but more like a 3-body effect. This is related to the 3-body Yefimov effect. So since these are not Yefimov tetramers, they have been called universal tetramers that are tied to Yefimov trimers. Interestingly, in this setting, it appears that because it's governed by the 3-body Yefimov effect, these states are determined by the 3-body parameter, which determines the location of these trimers. So once you know the location of the trimers with the 3-body parameter. Yeah.
We have a question of Johannes.
Okay.
He's asking, so 2 is a universal number?
To the number of tetramers. Yes.
Yes.
Yes. I mean, it's a universal result that there are 2 tetramers below each trimer for this bosonic system.
Okay. Thank you.
Yeah. And I should mention that actually the reason I plotted them here as dashed lines is because, strictly speaking, they are not bound states. They are resonances because they are embedded in the scattering continuum of a trimer plus 1 particle. So you have the various scattering thresholds defined by each trimer, and these tetramers here, they appear actually as resonances, but they are quite narrow, and they do follow a pattern similar to the ground state. Well, as usual, the ground state is has deviations from what universal theory would produce. So really, you get some kind of truly universal result when you go to the excited states. So these excited states are actually resonances. So actually, so concerning these ground states, the tetramers associated to the trimer ground state, to the ground state trimer, they could actually be seen experimentally, again, in these cesium experiments. So it's essentially the same technique in the same explanation that when you tune the scattering lengths and you are close to the appearance of these tetramer states, then you would have local enhancements of the loss, this time by 4-body recombination. As you can imagine, 4-body recombination is much less likely than 3-body, especially in these systems where the density is quite low by construction to avoid losses in the first place. But the experiments were able to actually see some small peaks. So this one, and then the second one appeared where it was predicted by, so it was first predicted by theory and then observed experimentally. The data is, very subtle. You have to trust the theory to perhaps to trust the experimental data, but you can convince yourself that there's some signal that corresponds to what the theory predicted. And then people looked at but this is for the ground states, which may not be completely universal. And then people look in more detail about the structure of these tetramer resonances. And they found that, okay, so we have, so close in this Borromean region, we have these 2 tetramers, but it turns out that the second tetramer actually dissociates into the trimer plus 1 particle at some point, and then kind of survives as a kind of virtual state, and then reappears at this point, and finally dissociates into 2 dimers. So the tetramer separates into two dimers. This is represented by, I forgot to mention, but this is the energy of a single dimer, and this is the energy of 2 dimers. And this is the universal pattern that repeats itself for excited states. There's an interesting thing happening here, although it's probably very difficult to observe. It is the fact that, as I mentioned, at this point, so we have a bound state between a dimer and a particle that makes this trimer here, right? So we have a dimer atom resonance. And so that means that if we consider now 4 particles, if we have the dimer and 2 particles, we have a resonant interaction around this point. We have a resonant interaction between a dimer and a particle. And so if we consider this 3-body system that is composed of 2 atoms and 1 dimer, we are in a situation where we can have the Efimov effect. So so far I've talked only about identical bosonic particles, and later we will see what happens for different kinds of particles. But I can already in advance tell you that There's also an Efimov effect for this configuration. So a larger particle, twice heavier particle that is resonantly interacting with these two particles. And so, but this is a rather unfavored situation. So that means that the spacing between the levels is very large, or rather, I should say, to go from the scaling ratio is very large. So that means that to go from the ground state to the excited state, you have to divide the energy by a very large number. So it's a rather unfavored situation. So it's very difficult, probably very difficult to observe. But in principle, there should be an infinite number of detrimental states around this point as well. So that's an interesting curiosity, that you can get the Efimov effect out of the Efimov effect itself. Okay, and then people looked at the what happens. Yes,
Professor Naidon,
yeah.
Tobias would like to make a
Okay.
question. Tobias.
Yeah,
Okay.
before going to more boson, Pascal,
Yes.
I just want to make a comment about this problem of new scales and so on, as you increase the number of bosons.
Yes.
I mean, you presented, it's a comment, okay? It's not just a comment that I think is important for people to have a more broad view of the problem, no? As, I mean, there is this discussions going on for quite a long time, involving many groups, including ours. But just a comment based on what you taught to us. So, I mean, the idea of having the geometric scaling comes, I mean, when you build the Skorniakov and Terma-Tyrosian equation, that of course, Efimov looked in his way with hyperspherical coordinates and so on. But it's important to remember also on the side of Minlos and Fadeev, also the work of Danilov, where he clearly showed the need of the three-body parameter at that point. What I want to comment is that the analogous construction for the four boson problem, or even more boson, is missing in the literature. And this, of course, will help on the side of the many calculations. I mean, our colleagues and many people have done, to have a clear picture on that. So at least in my view, we have to be a little bit more cautious. Maybe in a class of problems of Hamiltonians that people use with two-body, repulsive three-body forces and so on, you don't see evidences for other parameters or move this tetramer state, but it's clearly missing. I mean, the beautiful work that you showed to us, I mean, about the Skorniakov and Terma-Tyrosian equation, the same kind of thoughts is really missing for the Fadeev-Yakubovsky equations or for the tetramer problem. And therefore, I just want to put a word of caution, because the appearance of these new parameters has to do with the geometrical scaling, that you have the possibility of imaginary exponents. Essentially, is like that. So just to put a word of, I mean, of caution, that still this is not.
So you mean possibility of four-body effect?
Yes, four-body, maybe even five.
Okay.
We don't know. But I'm just saying that this kind of thoughts maybe has yet to be done. It's not easy, but is still open.
Yes. Actually, that's right. Actually, that's not the end of the story for this four-body Efimov effect, because as I will show later, there are systems where there's the four-body Efimov effect has been demonstrated. That's something I will come to. So and in that case, you need a four-body parameter. So I will show that example later. So indeed,
okay.
four-body Efimov effect is a possibility.
Not Efimov. I'm thinking about the Thomas, something that you are able to keep the Threebody, the trimer fixed, and then you see moving the tetramers below.
Okay.
So this is what I'm thinking. So for that, you need to analyze what happens in the large momentum region of short distances of the four-body generalization of the Skoniakov intermaterial sum equations. That is not an easy task.
Right.
We have been trying that. It's really
yes.
But there is a space yet to think about.
Right. Yeah. I mean, there are certainly points to yeah. I mean, this four-body problem is not easy. My understanding is that for this excited states here, for the ground state, I'm not sure, but for these excited states, what people find is that there are some potentials that in hyperspherical coordinates that can explain the existence of the state, and they happen at relatively large distances compared to the range of interactions. So they become insensitive to what happens at short range. So that explains the kind of insensitivity of these states to shorter scale. But if somehow this potential curve are different and they allow the probability to go to shorter distance, then in principle there could be some also some dependence, and you could this tetramer states could move. Yeah, I mean there are probably other points to explore.
Yeah, this is very interesting, all this physics, for sure. Very rich indeed.
Yes. Okay, so this was the result for 4 bosons, and then people looked further for a larger number of bosons, and it turns out that one can find pentamers. In that case, there are for the ground state, there are 3 pentamers, like so, 2 of them being just below the tetramers. I think this was only There was only calculated for this around this grand trimer state. The calculation is a bit involved for this excited state. So presumably the same structure repeats itself for this excited state, but I think this has not been confirmed yet. So we have this kind of indication. So there's an interesting, and then people have even looked for larger number of bosons, and they form, deeper and deeper structures. But mostly that is for in this region below the trimer state, for true bound states, for the resonance states around the other excited trimers, which should be in principle more universal if they behave indeed universally. But these are very difficult to calculate. Okay, so now, so we've been talking about bosons. Now let's look at other kinds of particles, mixtures of different kinds of particles. So we can have particles of different statistics. So we can have bosons, but also fermions. We can have particles of different masses. And we can also have particles in different spin states, different internal states. So first, let me give you a kind of table that summarizes all the results for these various mixtures. So, so first we can have either 3 identical bosons, so that's something we've seen already, or 2 identical bosons and another particle. It can be a boson or a fermion, it doesn't matter. The point is that it's distinguishable from these 2 bosons. Or we can have 3 distinguishable particles. And then the statistics does, I mean, at this Threebody level, the statistic doesn't really matter. They are just 3 distinguishable particles. So for all these cases, then we can consider the number of resonant pairs. So that means what is the interaction between these different pairs, and is it close to unitarity, close to two-body resonance? So there can be 3 resonant pairs, or only 2, or just 1. And for all these cases, it turns out that when there are 3 resonant pairs, then there is an Efimov effect. When there are 2 resonant pairs, there's also an Efimov effect. But when there's only 1 resonant pair, there's no Efimov effect. And this result actually can be understood intuitively from the mediated interaction picture I talked about before. So the idea that the Efimov attraction is a mediated attraction mediated by one of the 3 particles between the 2 others. And that works if we're in this situation, or in this situation, also this particle can mediate the interaction between these 2. But you see that in that situation, it's not possible to have a mediation at long range between 2 of these particles. So that's a simple interpretation of this result. Now, of course, the best situation is when we have 3 resonant interactions. And in that case, the scaling factor, as we've seen, is 22.7. However, when we have only 2 resonant interactions, the scaling factor is much larger, it's close to 2000. So that means that if you have a ground state, then the excited state has an energy which is 2000 squared smaller than the ground state. So that makes it very difficult to be observed. Okay, but this is the case for equal masses. So all these particles have equal mass, and then we can also consider the case when the particles do not have the same mass. So here, this is the case when there are 3 resonant interactions with 2 particles with the same mass and another particle with a different mass. So we can have either 2 light particles and a heavy one, or 2 heavy particles and a light one. So we can change the mass ratio between these 2 kinds of particles. So for the equal mass case, we have the scaling factor is 22.7. And you see that whether we change the mass ratio in one way or another, we actually can reduce this scaling factor. So we have a denser spectrum. So it's actually favorable for the Efimov effect to have particles of different masses. And in particular, the most favorable one is when there are 2 heavy particles interacting with the light particles, and that leads to a very dense spectrum of Efimov state with a very small scaling factor. And right, and we will see a simple understanding of this in terms of the Born-Oppenheimer approximation. Okay, so that was for this classes of 3 particles. Now there's the case when we have 3 identical fermions. So and by identical I mean in the same internal state. So what are called polarized fermions, and that we've seen already. We've seen that you cannot have the Efimov effect because they cannot interact in the S wave. Can only interact in the P wave, and then we've seen that the situation is different for P wave, so no Efimov effect. However, you can have the Efimov effect with fermions when they have different masses. So, so for this, you need 2 kinds of fermions and another kind of particle, which interacts resonantly with these 2 fermions like this. And in this case, you can have the Efimov effect, but provided that these 2 fermions are heavier than this particle. And Specifically, there's a critical mass ratio, which is around 13.6, above which you can get the Ефimov effect. So this is here 13.6. And at this point, you have an infinite scaling factor, and then the scaling factor gradually reduces as you increase the mass ratio. And for very heavy fermions interacting resonantly with another particle, eventually you get something similar to what happens for two heavy bosons interacting with another particle. So it's actually, as you can see, it's possible to have Ефimov effect even when you have some fermions in your system. And we will have a simple understanding of this with the Born-Haber approximation. So let's consider one particle interacting with two other particles with some resonant interaction. So these particles have mass capital M, and this particle has mass M. And for simplicity, we assume that there's no interaction between the identical particles. Of course, there can be some interaction, but this is just to understand the basics. And so, as I said, in this situation, what we can do is the Born-Haber approximation. So, as you remember from atomic physics, this is something that can be used when you have a system of very heavy and light particles, like the electrons around atomic nuclei. And in that case, because of this large mass ratio, one can assume that the large particle is faster than the heavy particles. And we can make the Born-Haber approximation, which consists in separating the motion of the heavy and the light in this way. So we assume that the wave function factorizes into the wave function for the heavy particle and a wave function for the light particle, but that is calculated in the presence of the heavy particles. So this is exactly what we do in atomic physics for example, an electron with two nuclei. So first, we solve the motion for the light particle in the presence of the two heavy particles. So that means that we solve the Schrödinger equation. So in general, there would be the kinetic energy and then the interaction with these heavy particles, which are fixed at some particular, with some separation capital R between these two heavy particles. And then solving the Schrödinger equation, we can get the energy of this light particle. So for negative energy, we can write it this way, minus h bar squared kappa squared divided by 2m. But you see this energy and the wave function depends parametrically on this distance r between the heavy particles. So if we do the zero-range theory, then we just have to solve the free wave equation, but impose the corresponding two-body boundary condition that describe the zero-range interaction between this light particle and the heavy particles. So once we solve this light particle problem and we obtain this energy as a function of for each separation between the heavy particles, we obtain this energy as a function of the distance between the heavy particles acts as a potential. This is the so-called Born-Haber potential. And we can use it then in the equation for the remaining part, which is the wave function between the heavy particles. Now we have the kinetic energy between the heavy particles and this Born-Haber potential, which is essentially the energy of the light particles in the presence of these heavy particles. So this is a two-step process, and then we can solve this Schrödinger equation for the heavy particles, and we solve the problem in this Born-Haber approximation. So if we apply the zero-range theory to calculate the energy of the light particles, one finds a simple equation for this energy, or for this wave binding wave number kappa, which is simply kappa plus or minus exponential minus kappa r, the distance between the heavy particles, divided by r, is equal to 1 over a. So this is something that you can easily derive by using the techniques we discussed before. And I leave it to you as an exercise. I think it's a good way to check if you understand how this zero-range theory works. You can derive it in different ways, actually. As we've seen, there are many flavors of the zero-range theory. You can do it in real space with the Bethe-Barres condition. You can do it in momentum space with the Bethe-Barres condition. You can use also contact interaction and renormalize it. So in the end, you get the same results. So you can try and do this simple calculation. I include the derivation in the slides, in the notes, so you can check the solution, but you can try for yourself. I think it's an interesting exercise. So then if we consider the lowest solution, it is given by in the case where this is minus sign. And consider in particular the limit when the scattering length is infinite, so the unitary limit. Then we get a very simple result that kappa r is equal to exponential kappa r. So this kappa r is just some number that is the solution of this equation. X is equal to exponential minus x, which you can calculate numerically. It's about 0.567, and it's connected to the value of some mathematical function, which I think is called the Lambert function. Anyway, this is just some number. So then you find the result that at unitarity between the light particle and the heavy particles, kappa is just some number divided by r. So if you put it back here, you see that now we see that the Born-Oppenheimer potential describing the effect of this light particle between the two heavy particles is minus a 1 over r squared potential, so an attractive 1 over r squared potential. And you see that you retrieve here the Efimov result, that there's an effective 1 over r squared attraction. And that's also supports the interpretation that I presented before in the case of three-identical bosons, that we can regard the Efimov attraction as a mediated interaction. So this is exactly what happens here in this limit of heavy and light particles. The mediation is achieved by this light particle, and it can be seen in the corresponding Born-Oppenheimer potential. Now, what I've done between this equation and that equation is that I consider a particular partial wave for this particular angular momentum, for this relative angular momentum between these two heavy particles. So that leads to this centrifugal barrier here with angular momentum L. And then I put the mass prefactor here on this side, so that we get here the mass ratio for this attractive 1 over r squared interaction. And now you see that in general there is so these two terms, they are proportional to 1 over r squared, and that's because they are both of kinetic origin. This is centrifugal repulsion, and this is Efimov attraction mediated by this light particle. And so they directly compete with each other, because this one is always positive and this one is negative when we consider this Gransey solution. So in general, there will be a competition between them. So centrifugal repulsion, Efimov attraction. So one thing that we can do is express the sum of these two terms in the same form as the one we obtained for the three identical bosons, in order to calculate an effective S0, which is then given by this expression. And that leads to an effective, and that will give the scaling factor that we obtain when we solve the bound state in this potential. Assuming that it's attractive. So let's assume that there's no angular momentum between the heavy particles. For example, if we have identical bosons, then there's no centrifugal repulsion, so the Efimov attraction always wins. So we always have the Efimov effect in that situation. And therefore, the physics depends not only on the scattering lengths, but also on a Threebody parameter because of this 1/r² attraction. And as you can see, it gets stronger for large mass ratio. So this is consistent with the results I announced at the beginning. But now we can also consider the case of two identical fermions in the same spin states. So then they must have at least one unit of angular momentum. So let's consider the case L = 1. And then we see that in order for this quantity to be positive, for this interaction to correspond to an attraction, because of the competition between the centrifugal repulsion and Efimov attraction, we get a minimum mass ratio. So you can solve for this equation for the critical value when this becomes 0, and then you get the mass ratio of 13.99 something. This is of course obtained in this Born-Oppenheimer approximation, which has very simple physical interpretation, but you can also calculate it without doing the Born-Oppenheimer approximation by solving for example, the Skolniakov-Mathiasson equation, and then you get the exact results that is 13.6. So it's quite close to the results found in the Born-Oppenheimer approximation. So we're having some earthquake in Japan. Earthquake. Maybe I will stop for a few moments.
Stay calm and seek shelter nearby.
Okay, just a second.
I hear an earthquake announcement in the microphone by Pascal.
Yeah, something. I didn't understand what happened.
No, this could be dangerous. It's an earthquake announcement.
Ah,
Okay. So it was true or not, but he canceled the microphone and he has to leave. I don't know. He's again here. Pascal, was the announcement of an earthquake correct?
Yeah, yes, there was an earthquake, so I could feel it before I heard the alarm. It was pretty strong, but now it seems that it's calmed down. So hopefully we can continue. I'm sorry about that. Yeah, this happens sometimes in Japan, as you know. So I think we can proceed.
Okay.
Okay. Right. So depending on the mass ratio, we can have the Efimov effect. And in that case, the physics depends on the scatterings and Threebody parameter because it goes to short distance. Or when the mass ratio is smaller than 20.6, then the Efimov attraction loses, and there's no Efimov effect. This potential becomes repulsive, and the physics depends only on A, on the scattering length, and does not depend on the short range physics. There's no need for a Threebody parameter. So in particular, when the three particles have the same mass, for example, if you have 3 spin 1/2 fermions, then you see that you are in the case where the Efimov attraction loses. So there's no Efimov effect, and so that's why there's no Efimov trimer of 3 fermions with spin 1/2. And you can think, for example, of 3 neutron. There is no such Efimov states because they have the same mass. And as a matter of fact, there's no evidence of tri-neutron. So that's consistent. So now let's have a look at the schematic three-body spectrum of these systems as a function, as always, as a function of 1 over the scattering length. So we have now a diamond state between these light and heavy particles. So close to the unitarity point, it has this universal behavior. The energy scale is like 1 over the scattering length squared. So if we consider 2 heavy and 1 light particle, this is the situation that is favorable for the Efimov effect, because the Efimov attraction is actually enhanced by this mass ratio. So we have a strong Efimov attraction, which means we have a high density of 3 body levels, which can be higher than in the case of 3 identical bosons. On the other hand, if we have the opposite situation of 2 light particles resonantly interacting with 1 heavy particle, again, I stress that there's no interaction between these identical particles. So otherwise it changes, it can completely change the situation. But if there's no or negligible interaction, then we are in the unfavorable situation with a weak Efimov attraction. So here I'm still using the equation we find from the Born-Oppenheimer approximation. Of course, this approximation is not valid in this case because we have a light particle, we have a heavy particle around 2 light particles. But anyway, just intuitively, you can understand that the Efimov attraction is very, very weak in that case. And so the Efimov effect may occur actually, but it's very, very weak, which means that we have very, very sparse spectrum. Also, the grand level may be very weakly bound. So it's interesting to consider what happens when you have more particles. So for example, if you have 3 heavy particles and 1 light, and they are with still the resonant interaction between the heavy and light, then the result is that was found by the researchers is that it's actually similar to what happens for identical bosons, kind of a generalization, although it's a bit more rich. But you can have, for example, this 2 tetramer states beyond below the trimer states. I don't fully remember the details, but it seems that in some particular regime, this trimer states actually dissociate. Yeah, so this is similar to what happened for the 3 identical bosons. This excited state can dissociate into the trimer and a 4th particle. Right, so this is for the case of this 3 heavy and 1 particle, 3 heavy bosons and 1 particle. Now let's look at the spectrum for when the particles are fermionic. So this situation is not, of course, not possible because the Efimov attraction is very weak, and we have, in addition to that, the centrifugal repulsion between these identical fermions. So there's no Efimov effect and no bound state. But as we've seen, when the mass ratio is large enough, larger than 13.6, this Efimov attraction mediated by this yellow particle between these red fermions is strong enough to win over the centrifugal repulsion between these 2 fermions. And then we can have, again, the Efimov effect. So depending on the mass ratio, we can have a rather dense Efimov spectrum of such trimers if the mass ratio is large enough. Now, the particularity of these trimers is now that they have 1 unit of angular momentum. So compared to the bosonic one, they also have some kind of 3-fold degeneracy, depending on the projection of this angular momentum. Now, if we consider a mass ratio that is smaller than 30.6, so there's no Efimov effect because mass ratio, the Efimov attraction is too weak. But a mass ratio that is larger than 1.17, it turns out that, so the reasoning I showed you before was actually right at unitarity. I took the limit when A goes to infinity to compare the Efimov traction with the centrifugal repulsion. But if we consider finite scattering lengths, then the station is a bit different. We still have a Efimov attraction, but it's 1/r² at small distance, and then it does something else at distances on the order of the scattering length. Even though we are in a situation where at short distance, the centrifugal barrier wins over this 1/r² attraction, so we have a repulsion at short distance, still at larger distance, the Efimov attraction wins. I mean, not 1/r², but the finite range scattering length, the finite scattering length effective Threebody attraction wins. So we can have a pocket of attraction that supports a finite number of bound states. And this potential is completely insensitive to the Threebody parameter because there's a centrifugal repulsion that dominates at short distance, and that prevents the particles to go to short distance where they would be sensitive to other things like Threebody parameter. So we have actually states that are described only in terms of the scattering lengths. And so that means that their energy must be proportional to the energy of the dimer. So it turns out that was found by this Kardachev and Malik that in this range of mass ratio, there can be up to 2 universal trimers that are described only by the scattering lengths, that their energy is proportional to that of the dimer. Okay, and below this critical mass ratio, then there's no trimer. So what happens when we consider more particles? Well, it turns out that if now we have 3 such heavy fermions, identical fermions, interacting with a light particle like this, resonantly, this particle is still able to glue these heavy fermions, like it was able to do so for these 2 fermions. It can also glue 3 fermions and form a 4-body bound state that is still described only by the scattering length. And that is when the mass ratio is between 8.86 and 13.384, so very specific mass range. And that was found by these people, Bazak and Petrov. And something interesting happens beyond this mass ratio. So if you increase the mass ratio, you make it, means that the light particles can move more freely between these heavy particles and can mediate a stronger and stronger interaction. And at some point, interestingly, this particle can mediate a scale invariant interaction, like in the Threebody Efimov effect. And this is the occurrence of what I mentioned before, the possibility of a 4-body Efimov effect, not with identical bosons, but with these mixtures of 3 identical fermions and a 4th particle. So this was found by these people, Kastamora, Prikopenko. So you see, this is really the definition of 4-body Efimov effect, that before the right at the occurrence of a 3-body bound state, there is the accumulation of an infinite number of 4-body bound states. Okay, so as you can see, this Efimov physics with, universal physics and Efimov physics with these mixtures of fermionic particles is actually quite rich, even more interesting than what happens for bosons. Okay, and finally, we can consider mixtures of two kinds of fermions with spin. So here, this is a bit similar to the bosonic case in the sense that we can have particles with different, either they are different nature or they are identical but have different internal states. So that means that they behave like distinguishable particles. So they can be in the fully symmetric wave function with no angular momentum and all interact with S-wave interactions. And if the interactions are resonant, then we can have an Efimov effect similar to that of bosons, although the masses may be different. So the reason why this is interesting is because it's reminiscent of two neutron halo nuclei in nuclear physics. So, so let me now talk about this halo nuclei. So here I represented the nuclei chart, which is obtained by changing the number of protons here and the number of neutrons. And then we can plot all the different kinds of possible nuclei. And so in the nuclear physics experiments, it was identified that among this observable nuclei, some of them have a very unusually large mean radius and very small binding energies. So that's something that was observed experimentally, and that occurs mostly for either proton-rich or neutron-rich nuclei. So, for example, here we have neutron-rich systems, and they are relatively short-lived elements compared to the stable ones, with lifetime of from 1 to 100 milliseconds. And the various experimental investigations found that they can be described as some compact core of nucleons surrounded by a few loosely bound nucleons. So for example, we can have this one proton halo state like this one, or one neutron halo state. So that means there's a neutron or proton orbiting at large distance a core of nucleus core. So this is why they're called halo nuclei, because they have this kind of halo structure, and it can be more than one nucleon. It can be, you can have two neutron halos like this examples. Right. So what I've shown here on this chart, so we have the blue ones are the one neutron halo, and the green ones are the two neutron halos, and there are even evidence of maybe 4 neutron halo nuclei. Okay, so when we look at this halo nuclei, it is very reminiscent of what we've been discussing in this universal Threebody physics. So we've seen that for resonant S-wave interaction, we can have this large S-wave dimer that are called halo dimers that could be produced experimentally in the laboratory with ultra-cold atoms. So this kind of one nucleon halo nuclei, they look very similar to this idea of halo dimer. And then it's natural to think that the two neutron halo nuclei, they correspond to Threebody systems that are similar to Efimov states. So are these halonuclei related to Efimov states? Well, at first sight, it looks like this is very promising because, in fact, all the conditions for having Efimov states are present. If you assume that this is indeed this kind of one neutron halonuclei manifestation of a halo dimer in the with large S-wave scattering length, then we can imagine that we have resonant interaction between this core and neutron. So, and we also know that we have nearly resonant interaction between the two neutrons with a large negative scattering length that is larger than the range of the force between the neutrons. So, so this is the first condition for the Efimov effect to occur, to have resonant interaction, and possibly we could have all three pairs that are resonantly interacting in such kind of this kind of systems. Also, we have the right conditions for the symmetry of the statistics of the particles. So they so we have distinguishable particles, this core and these neutrons, and these two neutrons, they are spin 1/2, so they can be different internal states. So this kind of system can have a fully symmetric wave function, like in the that is favorable for the Efimov effect. And finally, we also have different mass ratio that is different, that is larger than 1. So this core typically is much heavier than these neutrons. So all these are the good conditions for having the Efimov effect. So it's very tempting to think that these are manifestations of Efimov states. And so in that interpretation, then we could regard, for example, this barium-11 as some halo dimer. And then, interestingly, we would expect that when we add one more neutron, then we would have an Efimov state. So that means if we go back to the usual Efimov plot, let's say that we have one dimer here, then below this dimer, we expect to find Efimov states. So this barium-12, for example, would correspond to an Efimov state, probably the ground states. But actually, this is not recognized as a halo nucleus. And this could be understood by the fact that actually the Efimov states in these regions here are relatively compact because they are quite tightly bound in this region. So it's not inconsistent with the fact that they do not appear as some kind of halo structure. On the other hand, here for this lithium-11, where we remove one proton, or we change one proton into a neutron, it seems that we would be in a situation where we have an Efimov state that is now in this region, that is Borromean. So in this situation, you see that there is no corresponding one neutron halo. So that means there's no dimer. So that we are in this region, and so this would correspond in this Efimov state interpretation to a Borromean Efimov trimer. Okay, so now the question is this interpretation correct? So you see that actually this situation repeats itself again for around carbon-19. We have the similar situation. So is this interpretation correct? Well, it's difficult to say. So what can be done is to actually model this system by three-body systems, assuming that there's an inert core and neutrons, two neutrons, and input the corresponding interaction or scattering lengths. So as you know, in the zero-inch theory, we do not know the three-body parameter, so that's a difficulty. Nevertheless, people have been able to characterize possible candidates of Efimov states in these among these halonuclei and also some states that are not recognized as halonuclei. Of course, we've already seen the triton, which is the particular case. Actually, this core is just a proton here in this case. So we've seen that it's maybe regarded as something connected to a ground state ephemeral trimer, although that's not a very good example. Now, what about these ones? So the question is, how close are we to unitarity if this interpretation is correct? And as usual for natural system, it's quite exceptional to be very close to unitarity. So in most systems, actually, the corresponding scattering lengths would be either here, where there's only one trimer, non-Borrigan trimer. So that would be the case, for example, for this one or this one, as I explained, or sorry, this one. And the other possibility is to have a scattering length that is for which there's only one Borromean ground state trimer. So that would be the case of this one or this one. And then, but you see, the problem is that when we have only one ground state, it's very difficult to say whether it's an ephemeral state or not. We've seen this difficulty before because we have no other state to compare. So we cannot calculate any scaling ratio from experimental data. And there's the issue of the determination of the Threebody parameter. And also there's the issue that maybe these systems cannot be described as three-body bounds, as three-body systems, because this core actually is not a inert particle. It can actually be excited. It can react with these neutrons. So there are actually several difficulties. The basic, and also, as you remember, the ground state usually deviates from the zero in theory because of finite range corrections. So there are many difficulties for this system where there's only a ground state. So of course, the best we can hope for is we can have a system where we have not only ground state, but also an excited state. So if by accident, the interaction is such that we are either here or there, and in this case, we have two non-Borromean trimer states that would correspond to this case, carbon 22, or the case where we have two Borromean trimer states that would correspond to this state, carbon 20, which is not regarded as a halonucleus. Oh, sorry, I said I mixed. This one would correspond to the trimers, to the non-Borromean trimers, and this one would correspond to the Borromean trimers. So the Borromean trimers, they are much more weakly bound, so that's why they have a kind of a halo structure that is consistent with the fact that there is a identified halonucleus, whereas this one is not observed as a halonucleus, but that would be consistent with the fact that it corresponds to deeper region of this ephemeral spectrum. So only these two have been selected as possible candidates for having two trimers in the ephemeral spectrum that could be linked to these physical systems. So what we can say as of now, I think, is that the properties we know of these ephemeral systems are not inconsistent with, there's no inconsistency with what we see for this halonuclei or even some other nuclei like this one. So it's an interesting interpretation, but there are other models in nuclear physics that describe these states and these halonuclei, and which do not rely on ephemeral physics or this kind of three-body descriptions. As I said, there are many difficulties. Maybe, for example, for these systems, it could be that the ground state are actually outside the Threebody description because they are so tightly bound that they cannot be described simply by this Threebody states and Efimov description. But somehow the excited state would be more described by a Threebody structure that would conform to the Efimov states. But as far as I know, there's no definite confirmation that these are indeed Efimov states. I guess there needs to be more precise comparison between the theory of the universal prediction from the point of view of the zero-range theory. In particular, what is interesting to compare, and that can be accessed experimentally, is the geometric properties of this, the structural properties of the systems, and that has been already done. So as far as I understand, there's no inconsistency, but there's no clear evidence either that these halonuclei are Efimov states. But this is an interesting point that hopefully can be, hopefully there's a way to confirm this in the future. Okay, so actually, this is all I wanted to tell you for this lesson. So what time is it now?
It's 10 past.
Oh, I went past. Sorry, I thought
yes.
I had some time.
Any questions for Professor Naidon? I think there is in the chat. How big are the halonuclei compared to the instance, the electron orbit?
The electron orbit. So I'm trying to understand the question. Of course, we're not. Are you talking about in terms of actual comparison of length or some kind of scaling between the systems? You're asking if the halonuclei are larger than the orbit of an electron? Is that I mean the physical length associated to the orbit of an electron? Okay. Well, in that case, I don't have the numbers. Maybe the nuclear physicists can confirm, but I would not expect that, you know, even though they are halonuclei, they're larger than the range of the nuclear force. Still, the range of nuclear force is, I mean, the typical length scale is femtometers, few femtometers, and this exceeds this scale by maybe, I don't know, but I don't think it's a factor, 1,000 or 10,000. So I think we're still very, very, very small compared to the orbit of an electron. That would be my
can I
guess.
add, Pascal? No, yeah. Just a comparison that people does. Lithium-11 has only 11 nucleons. The size of the halo is this more or less comparable with the size of lead that has 238 nucleons or 200. So this is, I mean, is a very dilute system. I mean, the two neutron halo compared to the normal.
Can you say that again? How I didn't hear the. You said
the size of the halo.
The size of the halo, yes, is
of lithium-11 is the same size of lead nuclei that has I don't remember 238 nucleons.
Okay,
so
okay.
Very in that sense. It's a very dilute.
Very dilute. Yes.
Yeah, just to give an idea of size, not with the atom, but with another nuclei.
Okay.
And, so this halo, I mean, compared with normal nuclear matter,
Right.
It's really, really very dilute.
Yeah, sure. I mean, if you compare the nuclei themselves, but the question was about comparing with the orbit of an electron.
Yeah.
I would think that the electron is still far away compared to this.
Yes, for sure. Yeah.
But yes, for sure. I mean, these halo nuclei are remarkable. I mean, they're really different from the other nuclei. So they really have this halo structure.
Okay, any more questions for Professor Naidon? So, okay, so Professor, thank you very much for your lecture today.
Thank you very much.
We can finish.
Thank you, Pascal. Thank you very much.
Thank you everyone for attending, and see you in the final lecture.
Yes, thank you.